All right. Greetings, fellow scientists. I'd like to welcome you all to the Wisconsin Science Festival online field trip, the Physics Experience. Thank you for joining us today. We're ready to get started. My name is Gerard Buckner from the Wisconsin Science Festival, and we're here with our special guest, Mike Randall, for this field trip experience. So, how can you participate today? Well, you'll notice that your picture and audio are muted and that the chat isn't available. But if you have any questions you'd like to ask, you can use the Q&A feature. As soon as you have a question, go ahead and type that in right away, and we'll ask your question for you out loud during the field trip. This field trip will be recorded, and as always, we ask that you do this in all activities at the Wisconsin Science Festival with a responsible adult. We'd also like to thank all of our sponsors and partners that help that help make the Wisconsin Science Festival possible. You can find out more activities and events during the festival at wisconsinsciencefest.org. With that, we're excited to get started. Mike, you ready to take it away?
I am. Good afternoon, everyone. I'm Mike Randall, and I'm a giant ball of energy, as you can see on your screen. Well, no, not exactly. Let me move this around. I get to be my own camera person. So let's do that. There we go. Hi. I'm Mike Randall. I'm the president of the Physics Experience. Some of you may have known me. I used to do programming for the Wonders of Physics show there at UW-Madison. Today's show, oddly enough, is about physics. We're going to talk about what physics is, what it has to do with all of you. Mostly we're here to have fun today. Are you okay with that? Yeah, I'm going to pretend I heard you say yes. Okay. So the other thing I want you to really keep in mind is that you are a physicist. Yes, you. I'm talking to you. You're a physicist. You've been using physics your whole life. You're really good at it, okay? I'm going to show this to you several different ways today. Before we get into that, it's like, maybe we want to know what physics is. So here's my definition of physics. Now, physics covers a lot of different things. It covers sound you can hear. It covers light you can see. It covers movement. It covers electricity, magnetism, a whole bunch of other things. That's a pretty complicated definition. My definition is this. Physics is the study of stuff. Well, this floor I'm standing on is made out of stuff. This room is made out of stuff. You're made out of stuff. But scientists have a different word for everything. Scientists don't call stuff stuff. Scientists call stuff matter. So on the count of three, I want you to all say it with me. Okay, ready? 1, 2, 3, matter. Very good. 1, 2, 3.
Matter.
Very good. So physics is the study of matter. Like this ball. And physics is also the study of how you move stuff around. What gives you the ability to move stuff around? I'll give you a hint. It's a one-word answer, starts with the letter E. I think somebody said energy, right? Energy? Energy is it. Energy is the ability to do work. Energy is the ability to do anything. So physics is a study of matter and energy and how those two things play with each other, how they interact. And that covers all the things I mentioned earlier. It covers movement, like throwing a ball, covers sound, heat, light, electricity, magnetism. And by the way, it also covers another area called modern physics. I'm going to give you a really cool demo of that later with lasers. Okay, now the way this show works is you get to ask me what you want to see. Now I'm going to give you a quick tour here. I've got things over here that are high voltage with some explosions thrown in. I've got lasers. You're wondering what that basket is? It's a hovercraft. We get to move that around and play with that a little bit. I've got an air cannon there that we could look at. I've got a toilet paper shooter. I've got liquid nitrogen, some of my very favorite stuff to play with. And I've got a few other things that if you see something there that you don't understand what it is, you can ask me about it, okay?
We
So,
actually have a question. Mike, can I interrupt you for a second?
yes,
One
please.
of our anonymous attendees says, is the air matter too?
Air is matter. That's actually a really good question, and I have a demonstration for you on that. Let me aim over here for just a second. So, what scientists call stuff, if you take any piece of ordinary stuff and you break it into smaller and smaller pieces, you eventually get down to some little tiny things that sound like a boy's name. Atoms. That's right. That would be atoms. We're all made out of atoms. All ordinary stuff is made out of atoms, the stuff that you and I are familiar with. So how those atoms are arranged can be different, though. Sometimes, I've got a bunch of marbles in this bottle, okay? Sometimes the atoms are packed together really tightly. So they can kind of wiggle around a little bit, but they pretty much stay in place. What form of matter do you think that would represent? It would be a solid, like this tabletop, where the atoms are really tightly packed. Now, sometimes the atoms are a little bit more loosely arranged. So they'll fill up, they'll take on the shape of a container, but they won't necessarily fill it all the way up, and they can move past one another. What form of matter do you suppose that is? That would be a liquid, like the water I have in my drinking bottle. Then, to get to your question, sometimes the atoms are moving really fast. It might be moving too fast for you to see. So the atoms are moving really fast. They could fill up a container. They'll take on the shape of a container and fill it all the way to the top. This form of matter is all around us all the time. It's called air. So yes, that answers that question. Is air a type of matter? Absolutely. Right. Good question. And it's a good one to start with because we were talking a lot more about atoms, okay?
Oh, perfect.
All right. How's that? Okay. What's the next question? Who wants to
see asks, can we look at the air cannon?
Absolutely. Let me aim this over here a little bit. I get to be my own camera person, so I'm still kind of learning how to do that. So here's my air cannon. This is going to get a little bit noisy. So what we're doing here is I'm using electrical energy in this pump to push air into this special tank here. It's being stored up. Stored energy is called potential energy. That's important to remember. Now inside of this, I have a ball very much like this one. And when we get enough energy stored up, I could push this trigger and release all that air all at once. And we'll see what happens with the ball. Now this takes a little while to do this. And in the meantime, while we're waiting, you can think about where else in your life you see potential energy versus the kind of energy this ball has, which is called kinetic energy. Kinetic energy is the energy of movement. So stored energy is potential, movement energy is kinetic. Where else in your life do you see potential energy going to kinetic energy? Maybe you can think of a few examples. Okay, we're almost there. I'm going to hopefully aim at something that won't break. My wife would appreciate that. And I'm sure this is quite noisy. I hope it is. I like noisy things. Okay, we're there. Okay, in 3, 2, 1. Whoop, there it went. Wait a minute, let me get the ball. Check it out. Yeah, you'd look like that too if I shot you out of a cannon.
Absolutely.
So thank you for asking for that one. It's one of my newest toys, and it's one of my very favorites to play with. All right, what's our next? What do you want to see next? Remember, we got all this stuff over here.
Larry, I hope I'm pronouncing that correct, asked, what is the hovercraft? Or maybe where's the hovercraft?
The hovercraft is right there. And the thing is, all it is a wooden board with an air blower on it. So the way this works, and later on maybe I can show you what's underneath that, but just the idea is that the air goes under the board, and that air lifts up the board just a tiny bit. So here's the thing. Right now, let me aim back down here at the hovercraft. It's really hard to move this. So if I try, I really am pushing, and it's really hard to move. And it's because of a force called friction. You can try this yourself. Put your hands together like this and do this, okay? Take something to move against friction. Okay, so friction is a force. A force is something that it's like a push or a pull. So friction is a force that makes things want to stick together. So right now there's a lot of friction between the bottom of that board and the floor. So what we're going to do is by putting air into the board, it's going to actually, the air is going to lift the board up a tiny bit, but enough that the board and the floor aren't touching anymore. And all that nasty friction just goes away. And it looks, by the way, the stuffed animals are my wife's contribution, and I normally have kids writing this. Now it's really easy to move around.
Oh, that's amazing.
By the way, they're really easy to build. Obviously, with the supervision of adults, especially for running them, because they have no brakes and no steering. And to build one yourself, you have to use power tools. But you can also find online ways to make little ones. There's different ways to do it. Just look up like do-it-yourself hovercraft. There's some really fun ones. You can use balloons and old CDs or paper plates. Good
Nice.
question. Thank you very much.
Juliet says, "Can we see the laser?"
I have not a laser, I have 3 lasers, okay? And for this one, I'm going to turn the room lights out. I actually have this rigged up, so let me get aimed over here first. And I'm going to do several fun things with the laser, but we're going to aim at this screen first. I'll tell you more about that screen here in just a little bit. But let's turn the lights off first. There we go. Don't worry, I'm still here. So we have 3 lasers here. We have a red laser. We have a, oh, here we go, kind of a wimpy purple laser. And we have a shy green laser. My green laser, it's a funny thing, it doesn't like to be cold, and my basement's just a little bit cold, so it just takes a little time to warm up. But you can probably see it there. It's flashing on and off. There it goes.
Yeah.
All right, so I have 3 different kinds of lasers. Now, here's the important thing. Before I go any further, lasers like these make terrible, terrible toys. Can you
Why is
imagine
that?
why do these make terrible toys? Well, that
Are they
laser's
bad
pretty,
for our eyes?
yeah, that laser's pretty bright. If that laser shines on your eyes or on your friend's eyes or your pet's eyes, it can cause permanent blindness. Toys aren't supposed to make you go blind. Please, please, please don't play with lasers until you've gone to college like I have and gone and taken laser safety training. Seriously, I'm very serious about that. I mean, now if you have gone to college and you've taken laser safety training, they're a lot of fun. So we're going to use these lasers to try a few different things here. So first of all, I have another thing here. I'm actually going to turn my lights back on just for a second because I'm going to reposition this. Hang on. Lights on. I'm going to aim at this wall for a sec. All right. Yeah, that's perfect. Let me turn the lights back off. Now, like I said, I got 3 different lasers here. Here's my red laser. I also have a little thing here. It's a piece of plastic that when you look through it, everything looks like has rainbows around it. You probably have worn some of these glasses before. It's called a diffraction grating. And the diffraction grating actually bends light. That's why it makes everything look like rainbows. So if I shine a laser through this diffraction grating, now you see 1 dot. Ooh, now you see a whole bunch of them. See that?
Wow.
Isn't that cool? Now I want you to notice how big those squares are. Okay, that's the red laser right there. Let's try it with a different color. Let's try it with my purple laser. Okay, now you see 1 dot. Oops, hang on a second. 1 dot, many dots. See all that? But notice the size of the squares. The squares are smaller than they were with the red laser. Okay, let's try it with the green laser, shall we? See if my green laser's warm. There we go. Nice bright green laser. 1 dot, many dots. But the size is somewhere in between. So the red laser made the biggest squares. The blue laser made the smallest squares, and the green was somewhere in between. So that shows you that this diffraction grating bends different colors of light differently. That's why when you look through it, everything comes out looking like a rainbow. Now I'm going to go back and look at this other screen. The screen that's over here, and you're going to see it in a moment because it's dark in here right now, it's not an ordinary screen. It's a glow-in-the-dark screen, right? Now, you've all played with glow-in-the-dark stuff before, right? Before something glows in the dark, what do you have to do to it first? Well, you got to shine some light on it to charge it up, right? Now, this is where we get to talk about one of my favorite dead guys, Sir Isaac Newton. Sir Isaac Newton was a very smart guy. He lived a long time ago, which is why he's dead. Anyway, he's widely regarded as the father of physics, and he came up with a lot of great ideas about how the world works, including a lot of ideas about how light works. And for 200 years, everyone thought his ideas were it. But about 100 years ago, scientists were experimenting with light, and they got results totally different than what Newton predicted. And that's what I'm going to use this screen to show you why Newton and why the scientists were so freaked out by this. Okay, so now I'm going to turn the lights back off again and get my lasers out. All right, so glow-in-the-dark screen. To make it glow, I got to shine light on it. Well, Sir Isaac Newton would have said, hey, that super bright red laser thingy of yours, that is so bright that'll make that screen glow instantly. You know, that makes perfect sense. Except it doesn't work. Do you see any change? I don't see any glowing. I don't see anything happening. As soon as I turn the laser off, there's nothing. Huh. Well, that's weird. Well, you know what? Maybe this green laser, maybe it's brighter. Now that it's warmed up, it's super, super bright. I'll bet that'll make it. It doesn't do anything either. Huh. Well, that's weird. If Sir Isaac were here, he'd be freaked out right now because that's not what he would have expected. Well, the only one I got left is this wimpy purple laser. Shall we try that? All right.
Wow.
Self-portrait, glasses, beard, eyebrows, nose hair. Yeah, I know. I'm not a very good artist, okay? But why will this wimpy purple laser leave this beautiful green glowing trail and my green and my red lasers do nothing? You know what? It took another one of my favorite dead guys to figure this out. One of the smartest guys that's ever lived, and I bet you've all heard his name before. You ever heard of Albert Einstein? Yep. Albert figured this one out. He said it's not about how bright the light is, it's about how much energy is in the light. It turns out like purple light like this has more energy in it than green light. Green light has more energy than red light. What we see as different colors is really different amounts of energy in the light. And because he figured it out kind of recently, the past 100 years or so, that's why that's called an example of modern physics. Modern physics, by the way, is super important. So if you go to college and you study anything about modern physics, believe me, there will be lots for you to do. It's one of the most exciting areas of physics. Okay, great question. Thank you. I always love talking about lasers. All right, I'm also going to keep an eye on time here. We're in good shape. So what's my next question?
All right, Alina says, can you show us a liquid nitrogen, please?
I would be disappointed if we didn't get to it. Thank you for asking that up front, though. Oh, I love liquid nitrogen. I'm going to set up my camera, though, to look over at this corner here. That's where my liquid nitrogen stuff happens. Okay, that'll work. So, liquid nitrogen. You know what? I have a really bad habit of cutting my head off on camera. Let me.
Yeah, it's tough. This is a lot to manage.
I know. You know, it's like, what are you going to do? Let me see if I can move this back just a bit and angle it up just a bit. Is that going to work? Yeah, that'll work. See if I've cut my head off. Yeah, that just barely makes it. Okay, now, first of all, liquid nitrogen, like the lasers, liquid nitrogen is very dangerous stuff. Why is it dangerous? Actually, several reasons. The first reason it's really dangerous is it's super, 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 super cold. This stuff is 321 degrees below 0 Fahrenheit. That's minus 196 Celsius, 77 on something called the Kelvin scale. Okay, super dangerous. Now, if you want to play with this stuff, it's really fun, but you got to go to college first and you got to be trained in how to handle it safely and correctly. Got that? Now, if you know how to handle it safely and correctly, you can do this. This is full almost to the top. I can do that. Don't try it yourself. And I'm not even going to tell you how it works. Just say, learn how liquid nitrogen works and you'll learn about it. Now, it is super cold and you have to be very careful with it. But it's also it's a fun way to demonstrate some other principles. Now, I mentioned about solids, liquids, gases earlier, right? And the gases in particular, that's little atoms that are moving around really fast. What we didn't talk about was something called heat energy. You know, like rubbing your hands together, it feels warm. What is heat energy? Heat energy is how fast the atoms in something are moving. That's pretty much it. Okay, so if the atoms in something are moving around really fast, or if in a case of a solid, if they're just jiggling really fast, that means they're very hot. If they're not moving so fast, that means they're cooler. That's pretty easy to understand. So now let's do a little experiment, shall we? I'm going to put this balloon in the liquid nitrogen. What do you think is going to happen? Think about what I just said. The balloon's full of air. That air's got heat energy in it. I mean, there's heat energy in the room around me. What happens if we take that heat energy away? Is it going to pop? Let's find out. Keep your eyes on the balloon. Gerard, is anybody making comments on what they're seeing yet? Anybody notice anything yet?
See.
As soon as you see something happen, and let Gerard know, okay? What's it doing?
It's getting smaller.
It's getting smaller. Yeah, it's shrinking. So it sprung a leak, right? We're taking heat energy away from the air atoms inside this balloon. Those air atoms are now moving very slowly, which means they're not running into the insides of the balloon as hard. That means the pressure inside the balloon is going down. If we take enough heat energy away, the balloon will shrink down into this sad-looking thing. But all the air is still in there. And there's plenty of heat energy out here in the air in the room. So as the heat energy from the room goes back into the balloon, the air atoms inside the balloon start moving faster and faster. They start running into the walls of the balloon harder and harder. The pressure goes right back up. Pretty soon the balloon is right back to normal, just like nothing ever happened. Wow, you're showing off today. Okay, cool. Ta-da! Now, there's something, I said there were several things that were dangerous about liquid nitrogen, okay? Temperature is one of them. And it's like, it's so cold, if you don't handle it right, you will freeze your skin and go to the hospital with something really painful called frostbite. There's another danger to it too. If I took this one container of liquid nitrogen and I warmed it all back up to room temperature, this would make almost 700 containers of gas. So why is that a problem? Well, let's try this. Here's some liquid nitrogen in here. I'm going to put it inside this container, and then I'm going to seal it up. Don't ever try this, okay? Don't ever try this. And I'm going to actually have to do this on the floor. I'm now pounding a cork in the top of this, and
whoa.
Did you see that? So what happened there? As that liquid nitrogen was boiling and turning back into a gas, it took up a lot more room, which made a lot of pressure inside that sealed container. Eventually, it reached the point where it blew that cork out, like an explosion. Seriously, if you do this wrong, it could actually turn into a bomb, okay? Now, fortunately, remember, college, I know what I'm doing. Don't try this until you go to college and learn how to handle it correctly and safely. Hang on one moment. I'm going to retrieve that cork. It's amazing I haven't lost this. Now, you have to store this. Another thing you want to know about it, you have to store this liquid nitrogen in a very special container. This is called a dewar. It's super insulated. So I'm going to pour it back in here so I can use it for another show. But when I do this, I'm going to pour it back in here, and I want you to pay close attention to what this stuff looks like, okay? Now, this is not the liquid nitrogen. This stuff is so cold, I'm actually making a cloud right here in my basement. Can you see that? Look at that. I'm making a cloud. But that's not what I want you to look at. I want you to look at the liquid itself as I pour it back in. Can you be watching? Here we go. What's it look like, folks? It looks just like water. Seriously, don't drink it. Don't do it. It's bad for you. It's happened. People have done it. Just don't do it. It's really bad for you. Now watch this. Remember I told you earlier about not putting liquid nitrogen into sealed containers? By the way, you don't want to do that with dry ice either. Just don't do it. But now watch me. I'm sealing up this container. Ah, no, that's not a bomb. Remember I told you this is a special bottle? Any of the liquid in this container that turns to gas, that gas will leak out harmlessly. This will not turn into a bomb, but it does keep me from spilling it between shows, okay? Thank you for
Mike,
asking for liquid nitrogen. Yay.
Mike, when you were doing your cork explosion, Walter had a question. He said, "Is that why champagne explodes?"
Something on that order. In champagne, there's a lot of gas dissolved in the wine. It's like when you drink a soda, right? There's bubbles that come out of it. That's because that's a gas that's actually dissolved in the soda, okay? And sometimes those bubbles will come out, particularly maybe if the liquid gets a little too warm. When it gets warmer, some of that gas comes out, or if you bump it, sometimes that gas will come out in a rush. Or if you take the pressure off. So if you take like a bottle of seltzer water in particular and you loosen the cork, all of a sudden you'll see all the bubbles come out of it, right? So that's what happens in a champagne bottle too. As soon as you release that cork, or as soon as you bump it or take the wrappings off the cork, now there's nothing holding that cork in place. The pressure inside the bottle, bang, shoots that out, just like my cannon did, okay? Little different process though. Remember, in this case, it's a liquid. We got a liquid that's boiling and turning into a gas. In the case of champagne or soda, it's a gas that's dissolved in the liquid, and then it comes out of that liquid. It turns back into gas bubbles, and that's what builds up the pressure. So a
Nice.
little bit different process, but the same end result. Boom, which we like.
And let's see, from Nate, Evelyn, Rowan, and a few others, people want to know what is up with the toilet paper.
You're going to make me do the toilet paper one, aren't you? Well, I offered it. So here's the deal. One of my favorite scientists, his name is Bernoulli. Mainly because I like the name, Bernoulli. I just think it's fun to say, okay? But he was a very smart guy. He figured out something interesting about air. Is that when it's moving, when air is moving, it doesn't press down as hard. See, one thing that we forget, this is a really wild thing to think about. Right now, you are living at the bottom of an ocean. You really are. It's an ocean of air, okay? And the air around us is heavy, seriously heavy. See the end of my thumb? End of my thumb is about an inch wide and an inch high, okay? Any place I could cover with the end of my thumb, the air is pushing down with the weight of a bowling ball, okay? Right now I have a lot of bowling balls sitting on my head. So do you. Not literally, but it's that kind of force pushing on your head. So why don't we notice it? Well, guess the bowling balls on this side and the bowling balls on this side cancel out. So all the forces are in balance, okay? And we don't notice it. But sometimes you can do things that unbalance those forces and you can make interesting things happen. For example, if air is moving faster over a surface, then it actually means that there's less air pressure pushing down. You might have the same amount of pushing up from underneath something, but you don't have as many pushing down this way, and the surface will lift up. That's what makes airplane wings work, by the way. And it's also what makes this work. So what I have here is a roll of toilet paper, and I've got it set up so my air blower is going to blow over the top of that roll. So that means that the air pressure on top of the toilet paper will be less than on the bottom. So if the air pressure is less on top, that means I've created an imbalance of forces. What do you think the toilet paper is going to do? Shall we find out?
Let's see if we have any answers in the chat.
Oops. It sticks. There we go.
Wow, that's so cool.
Now I get to clean that up. See, normally
Yeah.
I do this where there's a whole bunch of kids in the audience. They clean it up for me. Now I've got to uncover my camera. I may have to figure out a different place to shoot this. So anyway, don't worry, I will
Awesome.
find some use for that. I know toilet paper is very precious these days. So
While you're cleaning up, Mike, we have a
yes,
question
go for it.
from Braylon. They asked, "What is your favorite type of matter?"
Favorite type of matter? Oh, that's easy. Now we've told you about solids, liquids, and gases, right? But you know what? Those are not the most common states of matter, not by far. If you look up in the night sky, 99% of what you see is this stuff. This is another state of matter, and it's called plasma. Okay? Plasma, if you take any ordinary matter, solid, liquid, or gas, and you dump a lot of energy into it, it could be heat energy, it could be electrical energy. You put enough energy into it, it turns into this. This is where, see, you want to understand something about atoms. Let me turn the lights off because that looks really cool. Atoms are made of even tinier things. If you could look inside of an atom, you would see some really tiny things. You'd see some things at the very center of the atom called protons, which have something called a positive charge. You don't need to worry too much about that. And there's neutrons, which have no charge. And then zipping around that nearby is something even tinier, little things called electrons. So if you take and dump a lot of energy into atoms, you can actually rip them apart. So what you end up with is atoms that are missing electrons. Those are called positive ions. And then the electrons themselves. So what you're seeing right there in this thing, which is called a plasma ball, is that mixture. It's a mixture of those positive ions and the negative electrons. And plasma does some really cool things. It conducts electricity, and it looks really cool. And I've actually done entire shows on plasma. So it's a really good question. I encourage you to learn more about it. In fact, one of the new demonstrations I'm working on sometime in the next few weeks, I'm going to have a musical Tesla coil ready, which uses plasma to make sound, like music. I can actually program it to play music. But yeah, look more into that. So like when you look at the night sky, 99% of what you see is plasma, which by the way is a good thing. Did I mention that you have to put a lot of energy into matter to make it into a plasma? If there was a lot of plasma here on Earth, we wouldn't be having this conversation because we'd be dead. We would not be alive. So it's a good thing we don't have much here. Quick question: where do you find plasma out in nature on Earth? Now, this is something that is man-made, but in nature, here on Earth, where do you see plasma? And the answer is lightning. Lightning is a form of plasma. It's made by high voltage electricity. And there's another one, if you count Earth's atmosphere. If you ever seen the auroras, like the northern lights, or if you're in the southern hemisphere, the southern lights, that's also plasma too. But that's about it. You generally don't
Right.
see plasmas in nature. Great question. Thank you for asking that. Okay, let's turn the lights back on. Who's next? We're gonna do like maybe one or two more demos, and then I'm gonna open it up for some. Well, actually, this is working pretty well. We're just gonna keep asking
Uh,
questions. All right, go ahead.
Braylon also had a different question. They asked, "What is the blue horn-looking thing?"
This is something to make you ask questions. I picked it up at a garage sale recently. It's a prop from one of the Despicable Me movies. It's a fart gun. Sorry. Sorry, parents. I got nothing. It's like, that's it. That's why I have it there. It's mainly to annoy my wife. All right. Now, I do want to save this. I am going to get to, oops, I don't have my camera aimed right. I am going to get to this. I'm saving this one for last, okay? So, because this is really fun.
Yeah, we have a lot of questions about that one. So,
Okay. Um, we are ending at 3:15. Is that correct?
yes.
Okay. I think let's get to something else first.
Okay.
And if we want to, since we're running low on time, I could actually pick something here. Since we're in the electricity area here, um, I mentioned something called Tesla coils earlier. Tesla is another one of my favorite dead guys. He's a very smart man who lived in early in the 20th century, and he's responsible for a lot of things that are important to our lives to this day, including how the electricity gets into our homes. It's something called alternating current. That was his idea. Um, he also invented something called a Tesla coil. This is a small Tesla coil. What this does is it takes those little electrons I mentioned earlier. So by the way, what electricity is, I totally skipped over that. Electricity is simple. All it is it's the movement energy of electrons. That's it. If you get electrons moving, you get electricity. Here's one way to do it. This is a generator. There's a magnet inside of this. When that magnet moves near a coil of wire, it actually moves those electrons along. Gives them a boost of that kinetic energy we talked about earlier. And that energy can do something useful like lighting up a light. Most of our electricity is made from gigantic versions of that, okay? What a Tesla coil does is it takes those little electrons and it shakes them back and forth really hard and really fast. It's called high voltage, high frequency electricity. And it looks like this. I'm going to turn the room lights off for you to see this. Okay. Am I close enough? Can you see that arc there?
Yes, we do.
Yeah, I'd bring my camera in closer, but I don't want to zap my camera. So, but you can see it from here. That's lighting up that whole light bulb too. You can see that little white arc there. So, wow. Now, does anybody think that spark is hot? Oh yeah, it's really easy to turn electrical energy into heat energy. And one of the places that happens is in your car engine. Now, most cars still run on fuel. I mean, we're seeing more and more electric cars, but most cars run on car fuel. And I've got a little tiny bit of car fuel in this. It's alcohol, but you can run cars on this. Now, this doesn't do anything unless you light it on fire. Well, in your car engine, there's a little thing called a spark plug. That spark plug makes a little spark like you just saw in your engine. That spark is hot, lights the fuel on fire, makes a little explosion, which pushes on a piston and eventually makes the wheels of the bus go round and round. You want to see this? Okay. Don't worry, I'm wearing hearing protection. And I think this one is another one too that's fun to do with the lights off. So remember, that's where it is right there. Okay, lights off. And in 5, 4, 3, 2, 1.
That's amazing.
I have no idea where the cork went. I'm sure it'll turn up later. Oh well. Again, usually this is nice doing this in a room full of people because I got lots of people who can keep track of it for me, but it'll turn up. Now, let's see. We've got time enough for this. This is called a Van de Graaff generator. In the wintertime, you ever rub your feet on the carpet and then touch a doorknob? Zap! You get a spark, kind of like what you just saw there. That's called static electricity. What you're really doing, you're scraping electrons off the carpet, you're storing them on your body. Electrons don't like to be stored up like that because they're always pushing away from each other. They repel each other with enormous force for their size. So as soon as you give them a way to escape, zap, they jump off you and make that spark you see. Now I have a machine here that does this for me. This is called a Van de Graaff generator. And it has a belt inside that runs around and moves the electrons from down here at the base up to the top. And it looks like this. Can you see those sparks?
Mm-hmm.
Here, getting some good ones there. Can you hear it? Can you hear the sparking?
Yes.
Okay, perfect. I was hoping it would come through on the microphone. All right, so you can do some really fun things with that high voltage electricity. One of the things, I didn't mention this at the beginning of the show. I used to be a rocket scientist. I'm not kidding about that. I used to work on the space shuttle main engines and other rocket engines, okay? So one of the newest ideas in rockets that is very exciting is using electricity to power rockets. It's called ion propulsion. And I happen to have one here. What's happening is, you can't hear it from where you're at, but there's the back end of the rockets have a little piece of wire coming out. And at the tip of that sharp piece of wire, you can see a little purple glow, and you can hear a hissing sound. And what's happening is that high voltage electricity is creating a little bit of plasma. And the plasma, the electrons on the wire and the electrons from the plasma repel from each other. Newton's third law is called the law of rockets. For every action, there's an equal and opposite reaction. So the ions go one way, the rocket goes the other way, just like a big rocket engine. Now, granted, I've worked with the space shuttle main engines, which are pound of the most powerful machines ever built by man. They generate 500,000 pounds of thrust versus, oops, got a little shock there. Don't worry, this is not dangerous. It looks dangerous. It's not at all. It's painful though. And in person, I like giving people superpowers with this. I can do that, but I don't have anyone here to do that with, so I'm going to do the next best thing. I'm going to show you the power of those electrons. Remember I said they like to push away from each other? So I got some aluminum pie pans here. So when I turn this on, this is going to be covered in electrons. This is going to be covered in electrons. Those electrons want to push away from each other. What do you suppose is going to happen? Let's find out. Yep, another mess for Mike to clean up. That's what's going to happen.
That was amazing.
Anyway, I just love that though. It's so much fun. I'm looking forward to when we actually get to go do in-person shows, because I literally give kids superpowers with this. I'll have kids stand on a ladder, little plastic ladder. They'll put one hand on here, and with their other hand, they point it out, and they can shoot energy beams off their fingers. Okay? Not anything dangerous, mind you, but it's something that's real. That whoever you're pointing at can feel it, they can hear it, they can even smell it. It's a smell called ozone.
We actually have a question about that. Kishin says, I noticed in the poster how a person's hair is spiky. Is it just a hairstyle, or what makes the person's hair change?
No, that's exactly it. Just like you saw with those pans, people's hair. So if someone's touching this ball here and you turn it on, so they get covered in electrons, right? So they got electrons all over their entire body and all over every single hair in their head. The electrons on this hair push away from the ones on this hair. As they push apart, it carries the hair with them. So the electrons carry it out. That's why on the poster you see that spiky hair. That happens for real. I've done that with hundreds, maybe thousands of kids. Longer the hair, the better. I once did a show with a girl who had waist-length red hair, and when we did that, she looked like this giant dandelion. It looked so cool.
Mariana says, wow, you should have a YouTube channel.
I do have a YouTube channel. Thanks for asking. I just started it. Now, it's not much of one, but if you go on YouTube and look up the physics experience, you'll find me. So I've done a few things on there. And please be in touch with me. If there's anything specific you want to see, I'd be more than happy to. I've been putting a lot of work into creating the studio space, but now that I've got it pretty well worked out, I'm thinking it's time for me to do more YouTube videos. I've also done a lot of programming for a lot of years with Channel 15 here in Madison. So if you go on their website, and again, this is not a plug for them per se, but if you go to nbc15.com and do a search for their videos, you'll see a lot of the 3 or 4 minute segments I did on their show. And in time, what I'm going to be doing is linking a lot of those videos to my YouTube channel. I've got their permission to do that. I just haven't got around to it yet, but I'll be doing that soon. But in the meantime, you can go on their website and find them for yourself. I've lost track. I think 70 or 80 different programs I did on their show over the years. So
cool. We have a minute left, so maybe we have time for like one question or two. Julia wants to know, going back to the orbital, why does it glow?
Why does the glow come out of the back of the rocket, or
the glowing function that you had when we first began?
This thing?
Yes.
The plasma ball?
Mm-hmm.
Remember, you put a lot of energy into that to make a plasma. Well, sometimes it's really easy to turn energy from one form into another. Okay, so you put electrical energy in, enough energy to rip the atoms apart into ions and electrons, and then in the process, sometimes those two get back together again. So the electrons will recombine with an ion. When they do that, they've got to dump that energy. It took energy to rip them apart. Now you've got to, when they come back together, that energy that's there has to go somewhere, and it comes out as light energy. Light is a form of energy. So that's why it's glowing. And it glows in very specific colors. And why it does that is another, boy, if we could get into that whole conversation about modern physics, that's a whole other side of that. But trust me, that is energy released when those electrons and the ions combine back together into regular atoms. Okay?
Awesome. Cool. Well, we
That, by the
are
way,
at
is also how fluorescent lights work, like this one. Same process. Good question. Really good questions. You guys are really sharp. You've been asking me really good questions today. What else you got? Or are we out of time?
we have a ton of questions, but we are out of time. So, Mike, can we send you these questions in the email?
I will get to as many as I can, but yeah,
Yeah.
absolutely. Please send them to me. I'd love to hear from you. And even if I don't get back to you personally, it will make a difference in terms of, how my shows go in the future. I'm hoping to do a lot more of these. I've got, now that I've got my studio set up in the basement, I'm looking forward to doing a lot more of these shows from here.
Awesome. Well, thank you so much, Mike, and thank you so much from all of our attendees today. You guys did an awesome job. Thank you for all the questions. This time went by so fast. And we have a bunch of more events happening this week. So again, be sure to check out wisconsinsciencefest.org and hope to see you there at all of our other functions.
Thanks
Thank
for
you, Mike.
coming, everyone. It's been my pleasure. Bye-bye.
Have a good day, everybody. Bye.